Welcome, everyone. This is the first of the Frontiers of Brain Health talks for this fall. We have a remarkable lineup of speakers that is sampling from a diverse set of topics, and we've reached out more widely across the U.S. for this particular semester. But we're delighted today to have our first kickoff Frontiers with David Lary, who is a faculty member at UT Dallas. Dr. Lary has a remarkable, distinguished academic history leading him to UT Dallas. He did his PhD at Cambridge in a field called atmospheric chemistry, and specifically he focused on photochemical computer modeling, which foreshadows his work that he would do later in his career, and he'll talk about today, fusing a variety of different methods together in order to develop models for prediction. At Cambridge, Sir David King endorsed David's appointment as a Cambridge University lecturer in the new field of chemical informatics, and that was the first chemical informatics department in the world. He received a Royal Society University Research Fellowship previously at Cambridge and was the first recipient of an Elan Fellowship at the University of Tel Aviv. In 2001, David joined NASA as the first Distinguished Goddard Fellow in Earth Sciences, where he was until 2010. He was appointed in 2018 to the U.S. Special Operations Command as a Fellow of SOFWorks. He is currently a professor of physics at UT Dallas and part of the Hansen Center for Space Sciences. So David's work is remarkably timely, especially with the California wildfires and fires in Oregon and the challenges of air quality that we're beginning to experience nationwide, especially in urban areas. This is a major challenge to our health. And one of the ways we can try to mitigate this is to do better data analyses, gather more data from the environment and gather more data from the individual. So there's a really critical data fusion problem that David is working on. And so he's impressed me numerous times with his machine learning, cutting edge algorithm approaches to integrating data and forming novel conclusions. Is exactly what we need to address this critical problem in health right now. So the way we will run this talk is Dr. Lary will present and I will manage the Q&A at the end of the hour. So if you can just hold questions till the end, or feel free to use the Q&A box as questions come up, and we'll get to those at the end. So we look very much forward to the presentation by Dr. David Lary.
So thank you, guys. I really appreciate the invitation, and I hope you'll enjoy this description of a journey of discovery that we've just embarked on together. So before I get carried away with the talk, I want to make sure I acknowledge my colleagues. And so I've gratefully listed their names at the bottom there. So this is very much a team effort. I think I would like to start by giving a motivation why we began this journey, because it seems quite an unusual title, Cognitive Performance and the Environment. It's becoming more and more apparent that the environment impacts us in numerous ways, and many of these are initially rather surprising. So I've provided here an assortment of recent scholarly journal articles and more popular press ones. So there's many articles recently that have titles like "Poor Air Quality Makes You Dumb." And then the more scholarly articles will say things like the impacts of air pollution on cognitive performance. So what we've tried to set out to do, and we're very much at the beginning of this journey, is to try and understand which components of the environment have the biggest physical and cognitive performance impacts. So that's actually quite a large and challenging task. So the way we've set out to try and do this is to comprehensively measure as much as we can of the environmental state, and at the same time measure as much as we can of the physical and cognitive state. So we obviously can't go around with something like an fMRI. That wouldn't be very portable, although it would give us very fine spatial resolution of the the state of our head. So instead, what we've opted to do is to use very wearable biometrics and to have a whole suite of these that we can take real-time data from. And so what's rather surprising is that normally we would think of air pollution affecting things like respiratory conditions, and indeed they do. But it's becoming increasingly apparent that cognitive and psychologically related conditions are being impacted by air quality. So this particular graph that I'm showing you here is from some work I did when I was still at NASA with the Graduate School of Nursing. And we looked at all the hospital emergency room admissions for all ICD codes over an entire year. And then I compared those or put them in the context of the environmental state for as many parameters as I have. So in the top left, you have a graph here which horizontally shows the abundance of airborne particulates, which we're going to look at in a little more detail shortly. And then vertically, the number of admissions of unspecified schizophrenia. And what was really remarkable is that these two seemed to track at least reasonably well. So as the abundance of the airborne particulates increased, so did the admissions with unspecified schizophrenia. And so initially that's rather surprising because we think of various respiratory conditions or even stroke or heart disease or cancers such as lung cancer being associated with pollution, and indeed they are. And the scale of this globally is actually quite staggering. The World Health Organization, this is one of their slides, estimate that outdoor air pollution leads to about 7 million deaths a year. And if you were to include indoor air pollution, this would increase to around 12 to 14 million people a year. So it's really a very globally important issue. And so these pollutants come from a variety of causes, like we're having the California fires right now, transportation. In fact, if you were to use the satellites to take a global picture, you could see the east coast of the United States with highways that run all the way up the east coast. You can very clearly see them from space in the abundance of things like nitrogen oxides in the air. So just to give us a sense of how big these particles we're going to start talking about are, I thought it would be useful to have a schematic. So grossly enlarged, you see across the back there a human hair, which is of the order of 50 to 70 microns across. And in the bottom left, you see some grains of sand, which are of the order of 50 to 90 microns across. So two of the criterion pollutants that the Environmental Protection Agency track are called PM 2.5 and PM10. So this PM just stands for particulate matter, and the number it refers to the size. So PM 2.5 would be the total amount of particles up to a size of 2.5 microns measured in micrograms per cubic meter. So you can see these particles are so small that you can get several of them, in fact tens of these smaller ones across a human hair. So it's probably useful to think of these particles as a Trojan horse. So not only can we breathe them in, as we'll see shortly, but on their surface there can be various metals and other chemicals which then are really unwelcome visitors that can get into the body, in fact even into the bloodstream, and some of them can get across the barrier into the brain itself. So these are really small, so the enlarged picture you see on the left in front of the Trojan horse is of the order of 1/10 of a micron in diameter. So these particles that we breathe in through our nose can get deep down into our lungs, as you can see schematically here, and they can end up causing a very large number of health effects. So the type of particles we're talking about, they can be from natural sources like windblown dust or pollen or even molds, or they can be from various anthropogenic human-caused sources, for example, from traffic and industry and so on. So as well as the psychological effects we're going to be looking at, they can also cause our eyes to water. It's like if anyone has seasonal allergies and hay fever, they're probably very familiar with. It can irritate our sinuses and so on. But probably what's not so obvious and apparent is the cognitive impacts they can have on us. So on the right-hand side, we see a schematic here which illustrates the two routes that these airborne pollutants can take to impact our cognitive function. So one would be the mechanical inhalation. They can, depending on their size, get deep down into our lungs and then even cross over into the blood. And then the response to this could lead to the body's response to the release of cytokines, which can then have some brain impacts, or they can go across through the olfactory bulb and affect the brain in that way. So this is a rather surprising thing where we don't talk about this really every day. And in popular culture, we have things like the Mad Hatter from Alice in Wonderland. Well, really, that's what was probably happening there is the hatters would use mercury a lot. That mercury could get across the blood, into the bloodstream and then into the brain, and that could there cause the cognitive decline. So here we have some slides of a rat brain, in fact, and this poor rat was exposed to pollutants for the previous 14 days. And you can see these pollutants have actually got into the rat's brain. So this is not hypothetical. This type of thing, unfortunately, actually happens. And so beyond that, it can cause oxidative stress, a whole set of different skin cancers, and other cancers can be caused by breathing in these particles. And probably one of the more surprising ones of all is there appears to be a gut-brain axis. And so the composition of our guts and our microbiomes can have cognitive impacts. So another route would be if we ingest particles, that can also have some cognitive effects. So what we're beginning to see, certainly beyond doubt, is that there are significant and complicated interactions between us and the environment. So it's probably an understatement to say trying to untangle these is rather challenging. So that's why we've opted for comprehensive sensing. And when it comes to the sensing of our bodies, we try to focus on our autonomic responses. So those are the responses that in large part we don't have conscious control over. For example, our pupil dilation. So right now, if we would look up at a light, over the order of a few milliseconds, our pupil dilation changes. But likewise, if we get emotionally stimulated in some way or even intoxicated because of something we've ingested or something we've breathed, that will also be affecting our pupil dilation. Likewise, there's the whole autonomic perspiration response, made famous from lie detectors and so on. And also our heart rate is an autonomic response. So probably the one influence we have over our autonomic system is our breathing rate. So we're essentially trying to measure all of these aspects as comprehensively as we can from a set of wearable biometric devices. And then, of course, we can have an interaction between the environmental state and whatever we might be doing at the time. So how good we are at cognitive tasks or arithmetic can be affected by the context we find ourselves in. And probably what's rather surprising is actually if we do a hard math problem, our pupil dilation responds on the same sort of time scale as it does when we look up to a bright light. So we would like to try and begin to disentangle these using a suite of biometric sensors. So on this schematic, you see the various sensors we're using. So all of them, apart from the sweat ones, we are currently using. So we're looking at our brain activity with a set of 64 electrodes from an EEG, skin conductance, heart rate, muscle activity, pupil dilation, blood oxygen. And so back to that math problem, if you were to do a hard math problem, you actually momentarily see your blood oxygen dip as you're doing that problem. So to give you a sense of what this might look like on a person, you can see in the bottom left some of these devices. So you see the EEG labeled 2 there. We have eye tracking glasses, which measure 100 times a second our pupil dilation, and so on. So each of these different sensors are giving us a different window onto the state of our autonomic responses. And we would like to then combine these with measures of the environmental state. So here we can see an example of what we get from the EEGs. So in the top right, you see one of the specific headset, in fact, that we're using. So there are 64 electrodes. They are actually being captured at 400 times a second. So these are measuring voltages on the surface of the scalp. And of course, that window into the brain is very much just of what's happening on the surface of the brain. And that electrical activity is coming from a very large number of neurons. And so what you see in those 4 different panels along the bottom are some of the EEG's data that we've captured, and it's split up here into 4 different frequency bands that are commonly used. But actually, we're also getting the data from each of these electrodes and considering them in much finer grain detail as well. So just to give you a sense of what this might look like, here are a couple of different people wearing these EEGs and the eye tracking glasses in one of the scenarios that we were measuring. So to give you a sense of what these EEGs, heat maps as we call them, look like, you can see one here. And one always has to be careful with the attribution of activity in a given part of the brain using the EEGs, because of course we're just seeing some of a picture of what's happening on the surface. But it turns out that the activity really responds depending on what task is being done. So it's very helpful to have the fine time resolution that the EEGs provide. So it's actually a finer time resolution than we would get from something like fMRI, but the fMRI would give us a much finer spatial resolution. So as we've seen that many of these biometric responses that we can measure could be being affected by more than one factor. So if we take, for example, our pupil dilation, and on the right-hand side, you actually see the live pictures or video that is being captured from our eye tracking glasses. And the glasses project an infrared grid across the eyes, and 100 times a second we're measuring pupil dilation, what the eyes are looking at, and so on. So as this pupil dilation can be affected by the ambient light conditions as well as any cognitive or other emotional encounters that we're having, we thought it would be good to characterize the role that the light is having so that then we can subtract that and more accurately look at any emotional or cognitive responses. So on the left-hand side, in those rather colorful diagrams which show wavelength horizontally through the visible spectrum, and so the color of light corresponding to that wavelength is depicted by the colors there, and vertically we have the intensity. So we see what the spectrum of daylight looks like, what sunlight looks like, what an LED spectrum of light looks like, and an incandescent bulb. So what we did was to then wear our eye tracking glasses, and at the same time very accurately measuring the light intensity in a whole set of wavelengths from 360 to 720 nanometers with a 1 nanometer wavelength resolution. So what we did was use our machine learning to build what we believe is the most accurate model to date of pupil diameter as a function of the light intensity. So schematically, we have across the top how the model is set up. So the green values you see in the boxes on the left are what our inputs were. So there was the light intensity or illuminance in more than 400 wavelength intervals. There was the orientation of the head, because it turns out that our pupil dilation actually changes as the orientation of our head changes. And then we would want to use this to estimate the values in orange on the right, the left pupil diameter, the right pupil diameter, and so on. So what you see in the left-hand panel here is the result of this. So the bar chart you see is machine learning returned to us the relative importance of the light intensity in various wavelengths. And what's interesting is it seemed that the most important wavelength for determining our pupil dilation is in the green, which corresponds, as you can see in the very lowest panel there, actually to the sensitivity of the various rods and cones in our eyes. So the scatter diagram you see, the colorful green and red diagram, is plotting horizontally the actual pupil diameter that we were measuring, the estimated pupil diameter rather, against the actual pupil diameter. So if our model was perfect, this would basically be a straight line with a slope of 1. And we can see actually it's really done a good job. So the green points are our training data set, and the red crosses is an independent validation, just to see how well we did. So the left-hand graph is for the left eye, and the right-hand graph is for the right eye. And what's interesting is there were slightly different wavelengths that were most important for determining the pupil diameter between the two eyes. They just differed by about 4 nanometers, but they were both still in the green. Now, when we compare this to the previous models, we actually can see that this is a remarkable achievement, because all those various background colors you see in cyan and blue were the analogous scatter diagrams for the previous models. And basically those previous models, it seemed, certainly in our case, were not doing a good job for being able to estimate the pupil diameter as a function of the light intensity. So we were very grateful for that. So I thought it might be interesting to show you this in a bit more detail for some time series of the pupil diameter as the subject, who's actually the graduate student here, was walking around. So in each of these graphs, vertically, we have the wavelength, and horizontally, we have time. And then the colors that you see were the light intensity at that wavelength. So as the student was walking around and he went from the shaded region into the sunlight and then also inside a building, the pupil diameter was rapidly changing between just less than around 1 millimeter up to about 7 millimeters. So it turns out that when we blink, we also pick up because of the muscle activity in the EEGs. So sometimes that is a bit of a contaminant in our EEG signals. So we wanted to make sure we can very accurately separate out when we have a blink. So it turns out that what's rather an obvious task like that hasn't been very well characterized, how you accurately characterize a blink. So, and one of the challenges can be with the eye tracking glasses is that depending on how our eye is looking, we don't always get the clearest view of the blink or not. So what we decided to do was to use a new approach called topological data analysis. And so that's what's depicted on the right-hand side. So you see those sort of skeleton structures that look a bit like a skewed Eiffel Tower. And it turns out that doing this topological data analysis, we could very clearly distinguish between accurately between the open eye and the closed eye. And being able to do that at a very high frequency, we can then use that information along with the EEGs to know exactly when we were blinking or not. So the basic idea behind this topological data analysis is that data has shape and shape has meaning. And that becomes important because we are actually considering a really high dimensional space here. So we have the real-time signals coming from the 64 electrodes. We have our ECG, our galvanic skin response, our eye tracking. But then in addition, for those EEGs, we're considering a very large number of frequency bands for every electrode. So it's of the order of around 16 to 20,000 variables a second. And being able to visualize those is sometimes challenging, to say the least. So I thought I would show you another example of how we've been doing this. So as you can appreciate, with 64 electrodes across the head and then all of those other frequency domains I was mentioning, this is such a high dimensional space that being able to visualize it is challenging. So what you can see here is one of these topological data analyses. And each of the circles that you see in these connected networks here is basically a set of records that have very similar signatures. And so what we can do is when you hover over one of these nodes, you can see the brain activity map. So I'm not sure if anyone has attempted this before, but we are really excited about embarking on this endeavor, and we hope that it will help us get very fine-grained insights to exactly what is happening moment by moment through these different encounters that we are studying. Now, it's not only those type of biometric parameters, actually the distribution of heat across the face and the expressions contain a lot of information. So what you see here is using, I guess, augmented reality. You see this lady's face and then superimposed on it the location of her veins. So as the blood flow changes across the face, so does the temperature distribution. And in addition, what we're interested in is using the micro expressions that we can characterize by the shape of the eyebrows and many facial landmarks to give us additional information. So to give you an example here on the right, we have a movie clip, and then on the far right, you see the gentleman's facial landmarks for every frame. So we've done the same here for the lady with the veins superimposed on her face. So those little dots you see hovering around are these facial landmarks. And so we can capture in very fine detail the micro expressions that can be very useful in looking at things like the cognitive state of the individual. And it's not just in states like this that we are going to be doing it, but also, for example, our cyclists that as we cycle around in the environment with these biometrics, and then at the same time we're measuring everything in the air, we're very interested to see if the blood flow across the face and these facial landmarks, as well as all the other biometrics, does that change when we encounter or breathe something in the environment? So let's switch gears now to how we're trying to characterize what's in the environment. So this is basically the time evolution for us. So this journey began for me back in 1987 and has continued up to the present. So we're using a set of 8 different sentinels to try and comprehensively capture the state of the environment, from the global scale that satellites provide us to the very local scale, like the street level sentinels we're deploying across Dallas, Fort Worth at the moment, and then even finer scale, things like the walking robot or the zero emission survey car, or a set of autonomous robots that can work together in a team that you might have seen in the YouTube video that might have been circulated. So this shows a picture here of a megacity, or often what's referred to as a dense urban environment. And this could actually be from the whole California fires, but in this case, the orange haze is not so much from a fire, but from the large levels of pollution. So we typically have surprisingly little information on what's in the air. And even if we do have spot measurements of what's in the air, we don't have good spatial coverage. So we're really trying to address that. So in much greater detail, we can look at the physical and cognitive impacts of this. So what you see here is one of our street level surveys. So this street level survey is across the Richardson and Plano and Garland area, and it's actually 10 by 10 kilometers. And this 10 kilometer by 10 kilometer region was chosen because it coincided to one of the satellite pixels on some of our earlier analysis. And so we wanted to answer the question, what spatial scale do we really need to be measuring the air quality to be getting a neighborhood scale view? And so the color of these circles corresponds to the abundance of the airborne particles. Blue is low and red is high. So you see there's a lot of spatial variability. So it turns out we really need to be making measurements every half a kilometer, at least, to characterize this. So with the typical cost of EPA sensors measuring air quality being from $100,000 to $1 million, that's really going to be hard to happen. And in fact, it explains why for the 7.5 million of us in DFW, an area the size of a New England state, we only have 3 sensors that the EPA provides for measuring airborne particulates. So we want to try and help with this. And so we're using a variety of strategies to get fine-grained observations, both by building low-cost sensors that we calibrate with machine learning against reference instruments, and in addition by remote sensing from weather radars and satellites. But it's not just the spatial scale that shows a lot of variability, the temporal scale does as well. So the inset in the bottom right actually shows our first complete day of size resolved measurements of these airborne particles. So horizontally we have time from midnight to midnight, but it's depicted in universal time. That's why the numbers look a bit strange. And the vertical axis is the size of these particles, from 0.8 of a micron to 40 microns. Now, I've shown this inset for a couple of reasons. So we can look at some things that the EPA typically don't by these measurements. One is that we look at a much finer time resolution of just a few seconds, and we see a lot of moment-to-moment variability. But also we extend the size range to cover the airborne molds and pollens, which are not normally measured at all by the EPA. And you might be able to see the band between 10 and 15 microns. There's like a cyan stripe across there. So that's actually airborne molds that our sensors are measuring. So here we have a suite of some of the platforms we're using. In the top left, there's one of our sensors on top of a Plano school. In the bottom right, there's our robotic boat in a Plano creek. In the middle, you see our zero-emission car, which has a whole load of reference-grade sensors in the back, including a mass spectrometer measuring everything in the air. And on the bottom right, we have our autonomous aerial vehicle, which is part of our robot team. And this is a very stable platform. In fact, it was built for filming movies. So it was the same robot that's used in filming Venom. And we actually mount on the bottom of it a hyperspectral camera that gives us, instead of like when we take a picture with our mobile phone, we get a red, green, and blue image that we combine to give us a color image. We actually have more than 400 wavelengths for every pixel. So for every pixel, we get an entire spectrum. So that allows us to look at the composition of the land surface and the water and so on. So We're also making measurements from bicycles, a whole range of different platforms. And so machine learning is becoming indispensable for us to combine this fire hose of data of the environmental state and the biometric state. So just to give you a sense of the number of parameters a second, from our environmental context, if you consider each of the size bands and the wavelength intervals and the chemicals we're measuring, it's about 2,000 parameters a second. And if you consider the biometric state, it's really upward of 20,000 parameters. So if we don't have some framework that can help us deal with this inordinate volume of data, it's really hard to disentangle. So that's where machine learning is very helpful to try and provide us the actionable insights into what's going on. So we're using a very large variety of these approaches, and I just mentioned some of the names here. And so, of course, these airborne particles cross over into another thing of current relevance with COVID. So here what you see is on the top left, that black cloud is actually a real photograph of a sneeze that was captured earlier this year in MIT. And there's some remarkable things associated with this. So I don't know if you realize that when we sneeze, our sneeze droplets can go up to about 27 feet, and they're traveling faster than a baseball. So the whole 6-foot social distancing right now corresponds to the distance the droplets come in our exhaled breath when we speak or cough. So on the right-hand side of the schematic, you then see these particles and how they penetrate down into our respiratory system. So if we use the cheaper masks, that will block the particles larger than 10 microns, but you would need something like an N95 mask to block the PM2.5. So this is also very relevant for things like that. And I couldn't resist showing you these slides. So these droplets that we exhale, this is a simulation of how they travel after they leave our body as a function of size. So the smallest particles are the blue ones and the largest ones are in red. So you notice that the large particles quickly fall down towards close to the ground, but the smaller ones will stay lofted for quite a time. So if you're going to go out walking or jogging, it's best to stand offset, staggered, rather than directly behind a person, because otherwise we're directly in the plume of their exhaled breath. So we hope to be able to extend even further some of the biometrics we do to look at, for example, the sebaceous oils and their content. So if you were to wipe behind your ear, those sebaceous oils actually they have a lot of information content in them, and so there's just so many additional things we would like to down the road explore, including the roles of diet and sleep and so on. So the goal of all of these studies is to try and give us actionable insights that can help us act in a way that will enhance our physical and cognitive performance. So just to close, I thought you might be interested in seeing some of our robots in action. So from this walking robot you see in the bottom left, we've been making measurements of the air composition. So you see it actually in one of the UTD buildings in the middle panel. So I think that's a good place for me to stop.
Let's first thank David for an incredible talk, really what amounts to a glimpse into the future of quantifying many aspects of our lives that almost certainly bear on our cognitive function and our health more broadly. Let's go ahead and move to questions. We have one of the first questions is, do you have a lab with graduate students at UT Dallas? And I think this might be potentially an inspiring student for you.
Oh, yes, sir. And in fact, most of the names you saw at the beginning were of the graduate students, and they've really done a phenomenal job. I'm very proud of them. So yes, we have a lot of fun with this stuff.
It looks like you have a whole set of skills needed for deploying these sensors around the environment with your collaborators. Another question I think that may be pretty specific to air travel, airplane pathways and their effect on the environment. Are you looking at comparisons before and after increases in noise and air pollution due to the FAA next gen airline paths and frequency? And the question notes that they had not done an impact study on that. So some concern about what impact noise and air pollution might have from air travel.
So for that specific aspect, I haven't done a study, but it's a statement of the obvious to say there is a significant impact of many modes of transport on the composition of the environment. And we probably had an unprecedented example of that recently with COVID. So you could see from space in the satellite measurements that both NASA and the European Space Agency make, and they make their data fully publicly available, which is really great. The clear before and after difference with the lockdowns. So there was a drastic reduction in the composition of the air. Now, for the practical insights, even though it's not for the air travel that you just mentioned, we are very much trying to address that. So the city of Plano asked us to build them a network of sensors. So we've built them and they're in the process of being calibrated right now. So soon there's going to be a set of 55 sensors across the city of Plano measuring air quality. And those are of two accuracies because cost is a sense. There are secondary standards and then our even cheaper tertiary ones. But we carefully calibrate each of these against reference instruments with machine learning. Now, those central secondary nodes, which are also the communication hub for the sensor networks, they also measure the sound levels. They actually have an upward-facing camera looking at the color of the sky. That's useful because we've all seen recently with the orange skies over California, the color balance and the composition of, as a function of wavelength, gives us an estimate of the airborne particles. And so we're actively doing that. And we also have microphones in there, not because we're not doing any sound recording like Big Brother's watching you, but rather for the sound levels, because that's a form of pollution as well. But also we hoping to deploy our machine learning on that so we can pick up different species of bird and animals. So many of our sensors will be located in association with Plano parks, for example. So as a byproduct, we hope to get like an ecological inventory of the various species of birds and animals. And also, if there were to be any gunshots, which we hope there won't be too many of those, we will be able to capture those and maybe get some information into which type of weapon was fired. And in addition, we're also measuring ionizing radiation. So we hope there's never another Chernobyl or Fukushima. But if there were to be a release of ionizing radiation, we would also be measuring that as well as actually lightning. So lightning is a source of some airborne nitrogen oxides and so on. Finally, we also measure the full spectrum of light because light is the ultimate driving force for much of the atmospheric photochemistry. So with these low-cost sensors, we've really tried to go to town with the machine learning in giving us the maximum benefit. So that was probably too long-winded of an answer, but yeah.
One of the other questions concerns functional near-infrared spectroscopy, a method of looking at possible absorption spectrums within blood, within the head, and a question about whether the particles that you discussed had wavelengths that could possibly be traced using an FNIRS methodology, and if you thought about that in the future.
Yes, that is very interesting. So we currently, because of limited resources, we don't have one of those instruments to play with, but we would very much like that. But this whole infrared spectroscopy is actually very much of use and of interest. So the aerial vehicle you see in the top right here, that's a camera dangling down beneath it in the middle. That's actually a hyperspectral camera which measures the visible and the near infrared. But if we are successful for some of the proposals we put in, we would like to actually have, in addition, another camera going further in to the near infrared and infrared, mid-infrared, just for the reason of looking at that spectroscopy. And for the boat, we also have a little infrared spectrometer made by Texas Instruments. It's very light and compact, that we were wanting to use to look at the composition of the water. So it's very much in keeping with that. It would be wonderful to, if we could identify absorptions that we can look at in real time. So it's akin to what I guess is done, but maybe different wavelengths for the blood oxygen measurements that are already made by ourselves, and also for many of these smart watches these days.
Fantastic. Another question concerns the pupil dilation effects, noting that that's extremely interesting work looking at light spectra and how they influence pupil dilation. I will echo that sentiment. I was amazed by your segment on the pupil modeling those influences on pupillometry, because when you go outside the lab, it's of course so much more variable, and being able to precisely quantify the effects of anxiety and executive function on pupil is so difficult to do. So what an amazing way forward that is using your modeling approach. A specific question related to that, can you make any inferences on how our current virtual work may be impacting our physiological and cognitive processes?
I don't have the results to do that, but I think it's interesting, and I will just share with you some of the things that have been on my mind because of the various encounters I've had. So I'm grateful to be a scholar at the Institute of Integrative Health in Maryland. And one of the other scholars there, he actually designed the lighting system for the space station. And so that uses very carefully controlled LEDs where you have a lot of control over the spectrum of the light. And the main motive for going to such extent to do that is that sleep dysregulation can occur from being exposed, especially in the blue part of the spectrum, for those times like late at night when normally we would be asleep. So and we've probably all done it and do it, if we pick up our mobile phone, say in the middle of the night, and we look at the screen, that blue glare is really not very good for us. So you might have seen on some vendors these days, they have a mode which it changes the spectrum at night to go more to the reds. But another thing he found was that he worked a lot with night shift workers, and the incidence of cancers for night shift workers was off the charts. And it seemed that being exposed to significant intensities of light at the part of the circadian rhythm where we're normally asleep can have major challenges. So one of the areas of interest to us were for those folks that, say, have to be in a constrained, dark environment, and they're having to do an analysis, say various analysts, whether it's for the military or otherwise, they're often having to make real-time decisions, but the surrounding environment may not be very conducive. So another project from the Institute of Integrative Health was for helping wounded warriors heal quickly. So they have this thing in Walter Reed Medical Center, which came out of that institute, where they, next to the creek, they actually put a whole set of places where the consultations with the physicians could occur in that much more tranquil environment. And also the color schemes within the rooms of the hospital, instead of being white, they would have like pastoral scenes and different shades. Instead of just the white, they would have more greens and so on. And it actually affects the speed at which people get better. So extrapolating from that, I think it really helps us if we make our virtual working environment as aesthetically pleasing as possible, because it seems these things do have a role, but I couldn't quantify it more than that.
Well, my own backgrounds are getting more and more aesthetically pleasing as weeks go on. I'm not sure if only I was actually in that real environment right now. Playing off that exact question that you just addressed about the potential to track health outcomes using these methodologies, are you focused mostly on short-term cognitive impacts of air pollution? Or is it also the goal to try to maybe longitudinally get a lot of samples to monitor performance against baselines? One of the things that we're really interested in. So can you just comment on your whether you see your work having more of a short-term cognitive differentiation, or I suppose how it might play out over the longer term?
So we would very much like to do both. So if we take the long-term one to start with, one of the challenges for the long-term longitudinal studies is the available data. If we were to take EPA sensors, there's only 330 sensors for the entire United States. So we've done a lot of effort trying to extend the spatial resolution of that by augmenting the data we get from the in situ sensors at those 330 sites with what we can get from remote sensing, either from satellites, which actually seems a very fruitful endeavor, and also from the weather radar. So as a side point, we're very used to the weather radars giving us information on the rain and the snow and the hail. And essentially the way it works is the radar is reflected by those micrometeors. But the same happens from the airborne particles, even in fact from insects. So if you have a weather front, often you'll get insects pushed in front of that front, and you see the radar reflectivity signal from the insects. So it seems that we get the best chance of estimating the size and the abundance of the airborne particles for particles up to 7 microns in diameter. And in fact, one of the ongoing studies for us by another graduate student, one has already graduated estimating airborne pollen with the weather radars, and another one is right now looking at estimating airborne particulates. So with those type of things, we can now get the neighborhood scale over multiple years, which is very much of interest to us for things not just like asthma, but also Alzheimer's and those other cognitively related conditions that seem to be affected by the pollution. But we can do a much better job for the short-term impacts because we have the comprehensive set of biometrics that you've seen, but also we can measure the full size distribution, in fact, from 5 nanometers up to 100 microns with just a few second resolution, as well as the biometric state. So for sure, all of those are of great interest. So we sometimes feel like a donkey between multiple haystacks. There's so much to do. So we always welcome partnerships. So if you would like to collaborate, we'd be delighted.
So on that note, we do have several inquiries about your lab and the potential to work with you. I think many people have been inspired by this, as well as potential collaborators. So as you know, we have the large-scale brain health project, which will be collecting longitudinal data from individuals over a period of many years, integrating some of these biosensors and the algorithms that reveal the relevance of things like air pollution and all of the remarkable things you've alluded to is hope. It's really a glimpse into the future. Amazing talk. I am immensely impressed with the sophistication through which you are evaluating both the individual and our interaction with the environment. So let's go ahead and wrap up here. I want to encourage everyone to join us again next week when we have Harris Iyer joining us, who's both a scientist and entrepreneur. He's the co-founder of the Prodeo Institute and is immensely interested in advocating for global brain health. So he is another big idea, big thinker who you do not want to miss. We are all about the leading edge of how we can lead healthier lives and how we can improve performance to achieve remarkable things for society. So what an amazing talk, and excellent speaker to lead off this fall semester. Thank you so much, Dr. Lary. And you will undoubtedly receive a lot of emails from potential applicants to your lab based on this new exposure from a variety of different areas.
Dan, can I ask one question?
Absolutely.
Yes. David, amazing. Oh my gosh, your work is so transformative. I mean, I'm not going to walk behind anyone.
I'm sorry.
I mean, in this time of COVID, you need to be on the front pages of safety. And I mean, the mask information, your information is so more scientifically driven, objectively, to help us change our behaviors. One of the questions that I had that I'm curious about, we're trying, as Dan mentioned, to find ways of measuring. I'm interested in the glasses and the pupillary response, because Dr. Ian Robertson is very interested in pupillary changes and the changes in the neurotransmitter norepinephrine. There's been an association, and we know, as when you were talking about the math problem solving it, that your pupils do that, and he says it's a signal of what's happening to the norepinephrine system that we would love to measure. Is that feasible with the glasses?
We would love to work with you on that. So the glasses work very well. They're made by a Swedish company called Tobii. We have the second generation of them, but they've actually just released also a third generation, which is even better. And the particular thing that we wished we could have had that they do in the third generation is they can work outdoors even better than the ones we have, because what happens is when you have high ambient levels of infrared, that interferes with the second generation. But the third generation ones, they've dealt with that. So for our cyclists, when they're outside, sometimes that's an issue. But indoors, they work very well, and we're using them in a set of studies. So we would be delighted on any of these things to collaborate with you. And
I think that the U.S. government needs to give you $1 billion, because you can help us solve COVID by some of the things that you're measuring. Thank you for this innovation beyond. I'm just like blown away by what you're doing.
Thank you. Just reminded me of the last one, which I'm so excited about, and I'm hoping we get funded, but we don't know yet, is also to look at the breath composition. Because it turns out we've already used it for looking at blood sugar, and you can see from the composition of the breath the blood sugar. So, but the minute we get infected with a virus, within about an hour, our breath composition changes. So that's a whole nother area that relates also to the gut-brain axis. So anyway, I shouldn't stop.
Well, you have to listen in on our other Frontiers talks, because we have one of the world's experts in gut brain, and I'm sure as you meet them, there will be ways that we can think about collaborating with you across these next few weeks. So
I'd love to. Please,
thank you, David.
Yes.
Tremendous.
Thank you.
Yes, everyone's extremely excited about your research and building more awareness of it. I think these kind of interdisciplinary talks can be really incredible opportunities. I can think of so many ways we could make use of that pupillometry precision. I mean, it could really bridge the gap between the lab and the environment in so many different memory and health-related tasks. So fantastic talk. It's given us a glimpse into the future and potential for amazing collaborations.
Thank
All right. Thank you, everyone.
Thank you.
Bye.